All right, let's summarize what we've decided our first derivative test is going to look like, and then let's try it again on a little bit messier function. So first thing, a reminder, derivatives and slopes are very closely related. So we know that if f prime is positive, then f is increasing. Positive slope means increasing function, and we know that if f prime is negative, then f is decreasing. And based on that, we can set up our first derivative test for finding local maximums and minimums. So if we are looking at our function and we're at a critical value or critical number, and our derivative changes sign from positive to negative. So positive first derivative is increasing, switches to negative, we're always going left to right, negative first derivative is decreasing. That's going to form a local maximum. Then f has a local max at x equals c. If f prime changes sign from negative to positive, that's going to form a local minimum at x equals c. So there are other things that can happen. We could have the first derivative be positive and then 0 or undefined and then go back to positive. That's not going to make a local maximum or minimum. Or negative and then either undefined or 0 and back to negative. Also not going to make a local maximum or minimum. That may make an inflection point. Sometimes that's what's going on there. Not always, but it can. But it's definitely not creating a max or a min. Okay, so your first derivative test is going to be to make a sign chart for f prime and then use these definitions below to decide what's a max and what's a min. So let's look at this function right here and find all critical values. So to find a critical value, you're going to take the derivative and you're going to determine when it's 0 and when it's undefined. So let's see, we're going to use a quotient rule here, and it's going to be maybe a little bit messy. We get x squared minus 2x plus 1 on the bottom. We get x squared minus 2x plus 1 on the top, and I forgot the square on the bottom. And then the derivative of the top is 2x plus 1. And then we need to subtract the top, x squared plus x minus 6, times the derivative of the bottom, which is a 2x minus 2. And that's pretty ugly. Let's see if I can do anything nice to simplify. I think if we got really fancy with our factoring, if we factored out all of these pieces fully, we might be able to do a greatest common factor trick and simplify this a little bit, but I'm guessing that not a lot of people would go that way as their first route. So let's just go ahead with what I think I'm more likely to see, which is picking up each of these and distributing them in, and you can go whichever direction you want. I'm going to distribute the smaller one in. So we will get a 2x plus 1 multiplied by the x squared, which will become a 2x cubed plus x squared, and then we'll get the 2x plus 1 multiplied into the negative 2x, so be very careful with that minus. I see negative 4x squared minus 2x, and then the 2x plus 1 multiplied by 1, that one at least is easy, plus 2x plus 1. And then we're going to be really careful with this one because it has a minus sign as well. So I'm going to distribute that in first. So this will become a negative x squared and a negative x and a positive 6. And then I need to run this 2x minus 2 through those parentheses. So it will distribute to the negative x squared, the negative x, and the 6. Okay, so negative x squared times 2x minus 2 becomes negative 2x cubed, and then positive 2x squared. Next is that whole thing multiplied by just a negative x this time. So we'll get a negative 2x squared and a plus 2x. And then last one, 2x minus 2 multiplied by 6. So I get a plus 12x and a minus 12. I got so close to fitting it in there. Okay, And then on the bottom, I have x squared minus 2x plus 1. You know what? I'm going to go ahead and factor that. The idea with the denominator is it doesn't have all the extra mess, but I do know that my goal is to try and cancel things out of the denominator. So if it's not already fully factored, get it there. And what's jumping out to me is that x squared minus 2x plus 1 factors into an x minus 1 squared. So we really have x minus 1 squared squared. Okay, let's see if we can at least get rid of some of this mess. I'm pretty sure I saw a 2x cubed and a negative 2x cubed. I do see a 2x squared and a negative 2x squared. I see a negative 2x and a 2x. Anything else that just full on cancels? I don't think so, but I can combine some things. So I have an x squared minus 4x squared. So that's a negative 3x squared. I have a 2x and a 12x. So that's 14x. And then I have a 1 and a minus 12, so that's negative 11. And that is all over x minus 1 to the 4th power. So let's see, can we get factors? So it would be factors of 33 that add up to 14. I think that is doable, 11 and 3. So let's see, I'm going to factor out the negative 1. And then, so it's negative here, different color, negative 3x squared minus 14x plus 11. Okay, so I need a 3x and an x. And then I think I want 11 and 1, because that'll give me my 3x and 11x, which add up to 14. And I want it to be negative 14, so both negative. Okay. Ooh, and I actually get to cancel one of these out. So I can get rid of a minus 1. So my final simplified derivative is negative 3x minus 11 over x minus 1 cubed. And that is my g prime. Okay, so we are now supposed to find critical values. Critical values happen when g prime is undefined or when g prime is 0. And you don't have to separate it like this. I'm just reminding you. So we want to ask ourselves, is g prime undefined? And the answer is yes, if x equals 1. But there's a tricky little caveat in the definition of a critical value. Critical value is a number that's in the domain of g that makes g prime 0 or undefined. So it's that domain piece that we have to be a little bit careful about. That original function is undefined if x equals 1 as well. So we're going to say, but so is g. And we don't count it as a critical value. The reason being, if it's not in the domain of g, it's not a point on the graph at all, let alone a local max or local min. So we're not interested in points that make the original function undefined as well. Here, what's happening is that the function has an asymptote at 1, which means there's definitely not a max or a min, and that asymptote is carrying through to its derivative. So that one doesn't count, but always check it. There are functions that will have undefined derivative that is a critical value. Okay, so instead we're just looking for g prime of x equals 0, which happens if 3x minus 11 is 0. What I'm saying there is that the only way to make a fraction 0 is to make the denominator 0, or you could think about it as you set the equation equal to 0, and then the first thing you do is clear fractions, which means multiply both sides by x minus 1 cubed, and that would get you here as well. So we want to add 11 and divide by 3, so my one and only critical value is at x equals 11/3. Okay, so this is the bulk of your work for your first derivative test for any messier function. For polynomials, that'll probably be pretty easy, but for a lot of functions, that's a little bit messy and it takes a while to get through. Now we're finally ready for our first derivative sign chart, which says, okay, we want to know what's happening around x equals 11/3. What we know is that g prime is 0 when x is 11/3, And even though it's not a critical value, I am going to mark x equals 1 on here because it is important to realize that that's part of your sign chart. The function could change signs there. And that's really because the function's undefined more than the derivative, but still, that's important to realize. The function is undefined here, so something weird could be happening. It is an asymptote. I don't really care what's happening to the left of the asymptote, so you could check over here if you wanted to. Really, I just care what's happening to either side of 11/3. So putting that 1 there is just making sure that I don't test too far to the left and get a bad answer. So let's see, 11/3, that's just shy of 4, 3 1/3. So let's plug in 2. And when I plug 2 in, I'm going for this simplified version of the derivative right here. So I would say if I plug 2 into the top, I get 6 minus 11. So there's a negative out in front. 6 minus 11 is negative 5. And then on the bottom of the fraction is, what is it? We're plugging in 2, so 1 cubed, which is positive. So if we have a negative times a negative on the top and a positive in the bottom, that ends up being positive. If you don't like this kind of shorthand, go ahead and write out what the numbers are. So a negative 5 on the top and a positive 1 in the bottom, and then you can do the arithmetic. Whatever you need to show there, but I want to see a little bit of something that tells me what you were doing. All right, and then 11/3 was just shy of 4, so we could plug in 4 or 5. Maybe I'll plug in 5. I have that negative out in front, and then when I do 5 in the numerator, I get 15 minus 11. So this time the numerator is positive, and then the denominator, 5 minus 1 is 4. So 4 cubed is going to be positive. This time I get a negative number. So my function, this is my function, not my derivative, was increasing and then hit a flat spot and then decreased. So I have a maximum. And let's see, by carefully decide whether G has a local maximum, a local minimum, or neither at each critical value. So there is a local max at x equals 2. So that would be my answer to this question. So that's all the way through one first derivative test. They won't necessarily take that long if your function's not so messy. Most of that time was in derivative finding, but they can, so you'll have a variety.